Everyone, welcome to lesson three. Today we're going to be talking about the conservation of momentum. Remembering that we are in unit three, momentum and collisions. You should have already done lesson one, which is about momentum, lesson two, which is about impulse, and now we're here. All right, some of our lesson objectives for today. We're going to start by defining Newton's third law of motion. This is going to be a necessary kind of review item that you guys will need to know in order to kind of move forward. We're going to review an example with momentum and impulse because all the things that we're learning are related. And then we're going to learn what the conservation of momentum is and show our knowledge of this content by getting all the formative questions correct. And you'll find those below. All right, so I just want to start with a quick little example of how can whales jump? Obviously, whales swimming in water. Don't find them chilling up on land. All right, for this whale to actually get up out of the water, something under the water must be moving in the opposite direction. And it tells us, right, if we're going to take this object with a ton of mass and move it up, then it must be moving with a pretty high velocity. So you notice that our whales have these big tails, right? As the tail pushes downward, a ton of water moves down at a high velocity. And the result is that the whale is able to then be pushed upwards. So you have water going down, whale going up. Now, this is really explained by Newton's third law. Newton's third law states that every single action has an equal and opposite reaction. Right? So when a whale moves its tail down, it pushes water down at a high velocity. The opposite reaction is that it causes the whale to move upwards. So we want to connect this to momentum. But again, just as a review, the action is tail moves water down, opposite reaction is whale moves up. All right, let's start connecting this to this idea of momentum and also kind of pull back one of our previous examples where we have this baseball or softball and a bat, right? So we know when a baseball is coming towards a bat and then the bat strikes it, we have another example of Newton's third law, right? The bat is exerting a force on the ball. The ball also exerts an equal and opposite force on that bat. Now, we know the time of the collision between the ball and the bat is like super short, right? Like 1/100th of a second. It happens like that. But within that snapshot, you have equal forces acting on both the ball and the bat. So what we're talking about at this moment, the moment when the ball hits the bat, is we're talking about the impulse, right? Prior to the ball hitting the bat, both of them have momentum. And then they come together and you have that moment of impulse. And we know that impulse is defined by force times the amount of time it took for that impulse to occur. When you have an impulse, then it means that there is a change in momentum. And we see that very clearly in baseball and softball. The ball is coming towards the batter, it hits the bat, and then suddenly the ball is now moving in a new direction. Now, one thing to kind of keep in mind is that the change in momentum of the bat is equal and opposite to the change in the momentum of the ball. And we'll kind of discuss how this is because we will notice that obviously, even though the ball is moving a ton and the bat is not, some of this can be explained. Let's start by breaking it down mathematically. All right, we need to consider that there's a momentum of the ball and the bat before the collision. All right, so let's establish that. We know we can find the momentum of the ball by finding its mass multiplied by its velocity. Probably going to have a low mass, high velocity. We can also find the momentum of the bat, right, while it's being swung. Have the mass of the bat, probably more than the ball, as well as the velocity while it's being swung. Okay, second, we need to consider when there's a collision, there's going to be an impulse, represented by a letter J. We know our formula for impulse is J, or impulse, equals force times time, right? The force is how much force is being applied on the ball and the bat, and time is how long that impulse occurs, right? Fractions of a second. Now, we saw in our last lesson that the impulse is going to be equal to the change in momentum. So same impulse acting on both the ball and the bat. Now, when we see this impulse, we calculate it, right? If we know the force, we know the time, we'll be able to know what the change in the momentum of the ball is. Right? We know that the mass of the ball is not going to change. So what's left to change? The velocity. Right? The velocity of the ball coming towards the bat is going to be different than the velocity of the ball going away from the bat. And same with the bat, right? We also have this impulse acting on the bat, right? So we have the changing momentum of the bat. The mass will not change, but the velocity will. All right, so mass of each object does not change. Therefore, it's the velocity and the direction of those objects that change. And we can explain this due to the fact that we have the law of conservation of momentum. All right. Again, just kind of further explaining this example, right? The change in the momentum of the ball is obvious because we see that it changes direction and it flies off at a greater speed than it was originally traveling. The change in momentum of the bat is not really obvious at all, right? Just kind of seems like the bat just continues swinging, right? Continues its same original momentum. That's not necessarily the case. In part because you have to consider which one has more mass, the ball or the bat. Considering that the bat is attached to a person, so we're talking about the mass of that, we need to think about the mass of that whole system, which is the bat plus the batter. Right. So even though you have equal and opposite forces acting on both the ball and the bat and batter, because the mass of the ball is so much smaller, that same force is going to affect it much more than it's going to affect the much larger system of the bat and batter. So therefore, the final velocity of the bat and batter is going to be much smaller than the ball, which is why the ball goes flying off out of the stadium and the bat does not. All right, let's look at it in another little example that's maybe a little bit easier to kind of understand, because this is where we get into talking about the conservation of momentum. All right, so we're talking about conservation of momentum. We really want to be looking at a closed system. So a closed system is really just where all the energy and momentum within a system that we're studying stays, right? So say if we have two objects, right, like these two billiard balls or pool balls, we're just considering those two balls, right? We're not considering anything else. This is our closed system. All right, so in this example of two pool balls, let's say if we have the momentum of ball A, this white ball, before the collision, we add it to the momentum of the other ball, the red oranges ball. That total momentum is going to be the same as the momentum of the white ball after the collision plus the momentum of the red ball after the collision. So you can see before the collision, the white ball is moving, but the red is not. After the collision, the white ball is at rest and the red ball is moving, right? So if we are adding that total momentum, it's going to be the same as the total momentum after the collision, right? This is called the law of conservation of momentum, and it's given by this equation here, right? Momentum of object A before plus momentum of object B before equals the momentum of object A after plus the momentum of object B after. Now, again, it's not limited to just two objects, right? We could have 100 objects in here, right? And the total momentum before and after would be the same. So keep in mind, this is just important to know that even though momentum of both these objects change, we're looking at the total momentum of the system being added together and having that before and after collision. In here, it's a little video showing momentum and some collisions. And kind of cool part about this video is it's shot in the International Space Station, so it's being shot without any type of gravity. So it's a short little video. Go ahead and watch it. Give you a little more in depth and some visual examples of what we're talking about. All right, let's look at a mathematical example problem, right? Kind of similar to the two pool balls. Say we have ball A, right, has a mass of 2 kilograms, right? We know if we want to know momentum, we need to know mass. It's moving due west with a velocity of 2 meters per second. Now, if you remember, if we want to know momentum, we need mass and velocity, right? It's going to be mass times velocity. So 2 times 2 is what? 4. All right, and that's before any collision, before anything has happened. Ball B has a mass of 4 kilograms and is also moving west with a velocity of 1 meter per second. So again, same thing. Momentum of ball B, mass times velocity, 4 times 1, has a momentum of 4. Okay. Ball A is moving faster, so it overtakes ball B and they collide from behind. So they are both moving in the same direction. Ball A hits ball B, right? So you get something like that. After the collision, ball A is now moving westward with a velocity of 1 meter per second. We want to figure out what is the velocity of ball B. Now, again, we can pretty easily figure out the momentum before, and we know that ball A had a momentum of 4, ball B had a momentum of 4, so 4 plus 4 is going to be 8. Right? So we know that the total momentum after is going to be 8. The only thing left to find is going to be the velocity of ball B. So let's go ahead and just kind of break down the mathematical steps. Again, as with any example problem, I suggest you guys kind of write this down in your notebook just so you have a step-by-step explanation of how to solve these types of problems. Okay, so you can set up our problem, right? We know that our formula is momentum of ball A before plus momentum of ball B before equals momentum ball A after plus momentum ball B after. So that's our formula. We can just plug in all our numbers. Again, the only number we don't know is the velocity of ball B here. All right, so we plug it all in. We can begin solving. All right, we know that the velocity before is going to be 4 plus 4, which is 8. On the other side, we have 2 plus 4v, right? It's missing. So we can kind of move some terms around. So we got 8 on this side, 2 on this side. We move the 2 over here, so we get 8 minus 2. So we know that the velocity or the momentum of ball B is going to be 4 times our velocity. That equals 6, right? Divide 4 by both sides, and then we get 6 divided by 4. So our velocity of ball B after is going to be 1.5 meters per second. So our velocity of ball 1 actually slowed down, right? It was cut in half. And the velocity of ball B actually sped up. Now, if we were to make a visual example of this, right, we would have the slower ball in front, the faster ball in back, right? After the collision, the velocity of ball A is now cut in half, and the velocity of ball B has increased by 50%. Okay. We have this simulation here. We've done it a couple times. Again, we're kind of seeing it in a few different scenarios. In this one, you can see how our energy and momentum exchange during a bumper car collision, right? Kind of instead of having 2 balls colliding, we have 2 bumper cars. You can move the different sliders in this interactive to kind of change how elastic each of the cars are. And we'll talk about elastic and inelastic collisions in our next lesson. And also you can change the masses of the different cars, which will also affect their energy and their momentum. All right, just as a quick summary, when we're talking about conservation of momentum, it's within a closed system. Again, a closed system is one in which both objects exerting a force and object receiving the force are within the same system, right? In a closed system, momentum is always conserved, right? We don't lose any momentum. We don't create any new momentum. The momentum before is always going to be the same as the momentum after. And so kind of given by this formula below. We do have a few kind of additional readings, right? A lot of the materials for this particular lesson were taken from this first reading here. If you want to add a little bit more math and kind of look at it in 2 dimensions, right, when we're kind of pulling in angles, you can read the second article. Again, kind of all of it is summarized in this Khan Academy article if you really want to dig in a little bit deeper. So feel free. Guys, there's a few formative questions below. Go ahead and start answering those. Again, you need to get all of them correct in order to move on to the next lesson. All right, let me know if you guys have any questions, and I will talk to you guys later.